Hello and namaste. My name is Brandon and welcome to the next video in my series on basic time series. In this video, we will learn about the exponential moving average, taking a very visual approach to the topic. If you like this video, please like, comment, share, and subscribe. Let's get started. So here is the data we've been using up to this point in this series. It is Nigeria's GDP per capita from the year 2000 up through the year 2020. We put it on a chart and it looks like this. So the task in this video is to create an exponential moving average for this data. First, let's learn about what the exponential moving average actually is and what makes it different from other methods we've learned about. So the exponential moving average, or EMA technique, has a new trick up its sleeve as compared to the naive forecasting method, the simple moving average forecasting method, and the weighted moving average forecasting method, all of which we have covered in prior videos. The naive, the SMA, and the WMA only use past actual values to make their forecasts. However, the exponential moving average also incorporates the prior period forecast. It achieves this by mixing the prior period actual value and the prior period forecast value using two weights that sum to 1. The result is that mathematically, the exponential moving average is comprised of all past actual and forecast values. That's what makes it different. The weights for prior period actual and prior period forecast sum to 1, and that sum is split into two components: an alpha smoothing factor, represented by the Greek letter alpha, and a dampening factor, which is 1 minus alpha. Of course, alpha is between 0 and 1. The term smoothing factor is a misnomer, however. When alpha equals 1, the exponential moving average is identical to the naive forecast, so less smoothing is actually occurring. When alpha equals 0, or the dampening factor equals 1, the forecast is a horizontal line at the value of the starting forecast. It looks very odd, and we'll see that here in a minute. It is literally dampened into a flat line. So Excel's Data Analysis Toolpack add-in asks for the dampening factor, so it can be confusing. You might be working a problem for your homework or working some sort of problem, and you're trying to find the alpha value. However, the Excel Data Analysis Toolpack actually wants the dampening, so it's 1 minus alpha. So keep that in mind if you are an Excel user. The effect of the change as alpha goes between 0 and 1 is not linear. As alpha approaches 0, the effect on the forecast becomes increasingly drastic away from the naive, and that should make sense. This is an exponential moving average, so the steps between 0 and 1 with respect to alpha are not linear, and we'll see that here in a minute visually. So you as the analyst ask yourself this question: how much do I think the forecast value for the next period is related to the actual value from last period? Now, if you think that is quite a lot, then select a large alpha value as it moves the EMA closer to the naive forecast, and at alpha equals 1, the EMA is the naive forecast. If you think moderately, then select a midpoint alpha, such as alpha equals 0.5 as the starting point. That is an equal weighting of the prior period actual value and the prior period forecast value. It's a 50-50 split between the two. Now, alpha can be optimized using linear programming, for example, Solver in Excel, if the time series is stationary, but it is often trial and error. So here is the EMA formula. Luckily, it's pretty simple. So f sub t plus 1, that just means the forecast value for the next period, is equal to alpha times y sub t, that's just alpha times the actual value from last period, plus 1 minus alpha, the difference, times the forecast value from last period. And visually, this will make sense here in a second. It's actually very simple. F sub t plus 1, forecast of the time series for the next period. Y sub t is the actual value of the time series in period t. F sub t is the forecast value of the time series in period t. And alpha is your smoothing factor or smoothing constant, which is between 0 and 1. So luckily, mathematically, it's a very simple formula. Now, if you look at that formula closely, you'll notice there's a very interesting thing about it. So due to the chained nature of the EMA calculation, an interesting thing happens. The EMA forecast for any period is a weighted average of all the previous actual values in the time series. So the exponential in exponential moving average refers to the weights assigned to those past values. And all those weights sum to 1. The allocation of weights is determined by alpha across the past time values. There are many resources that walk through the mathematics of this, but if you take a look at that formula, you will see that what happens over time is that the prior actual and the prior forecast are always integrated into the rolling forecast. And therefore what happens is that the EMA ends up being a weighted average of all the previous actual values. Now that we have the concepts down, let's get to the visual part of this video. So over the next several slides, here is what I'm going to do. What I'm going to do is create exponential moving average forecasts with different levels for alpha. And what I will do is morph the slides one to the other so you can see the change that's happening. Let's start here. Alpha equals 1. This first line is the actual data we saw at the beginning. It is Nigeria's GDP per capita over that time period. Here is the exponential moving average forecast for alpha equals 1. Well, that might look a bit odd to you. It looks like it's just the data points in the original data shifted over one time period, and that's because it is. So at alpha equals 1, we are putting all the weight on the prior period's actual value and none of the weight on the prior period's forecast value. So when we put all the weight on the prior period's actual value, we have another name for that. It's called the naive forecast. And you can notice here that that line is not very smooth physically either. Alpha equals 1 is the same as the naive forecast. It is just the original actual values shifted over in time. Now let's change alpha to 0.75. So notice the gap between the actual and the predicted values grew. So what's happening with the weights here? Well, since alpha equals 0.75, we are assigning 0.75 of the weight, or 3/4 of the weight, to the prior period's actual value. The difference of 0.25, or 1/4 of the weight, is being assigned to the prior period's forecast value. And this is what we get. Now let's change it to 0.5. Again, the gap increases. Also notice that the line is physically smoothing as we go. So in this instance, we are assigning half the weight to the prior period actual and half the weight to the prior period forecast. But again, notice the gap between the two lines is getting larger, which is what we don't want. Now let's change the value to 0.25. Same thing. So now we are assigning 0.25, or 1/4 of the weight, to the prior period actual value and 0.75 to the prior period's forecast value. And again, in this instance, the gap grew between the lines, at least there in the first part of it, which we'll get to why that is here in a second. And also notice that the line is physically smoother here as well. And finally, let's do the extreme. Let's change the alpha to 0. Well, that is very weird. Why is it doing that? Well, remember, when alpha equals 0, we are assigning 0 weight to the prior period actual. We are assigning all the weight to the prior period forecast. So, in that first data point there, we are assigning a value of the prior period forecast, which in this case, remember, we just move it over one period. And then because we're assigning all the weight to the prior period forecast, it does that for the entire time series. So that's the extreme. On one extreme, when alpha equals 1, it is the same as the naive forecast. On the other extreme, when alpha equals 0, it's just the original forecast value horizontally spread across the entire time series. So comparing values of alpha for different exponential moving averages, this is all that information just on one graph. So we have our original data there in the green line. We have our alpha equals 1, which is the same as the naive forecast there in the blue. Alpha of 0.75 in the orange. Alpha of 0.5 in the lighter green there. Alpha of 0.25 in the yellow. And an alpha of 0 there in the pink. So you can see what I said before, that this step from 0 to 1 or 1 to 0, depending on which direction you're going, is not linear. So the difference between an alpha of 1 and 0.5 is one thing. The difference between alpha of 0.5 and 0 is very drastic. So it's not a linear change as alpha changes. High alphas emphasize prior actual values. Low alphas emphasize prior forecast values. Here's that same graph zoomed in. The thing here is that due to the strong trend, the exponential moving average closest to the naive forecast continues to be the best. And one thing about the exponential moving average is that it does not do well with time series that have trends in them. While we won't get into it here, there's actually a technique that deals with this called Foltz method, H-O-L-T, Foltz method, that deals with the trend in an exponential moving average, but we'll get to that later. In this case, because of the trend, the alpha equals 1, or the naive exponential moving average, continues to be the best. Now, where do the forecasts seem to converge? Well, they converge over here on the right, towards the end. Well, the question is, why? Well, that is where the time series flattens out somewhat. So the time series there in the green goes up, and then it kind of peaks, and then it goes down a little bit, but it's relatively flat. Once the time series pretty much flattens out, all of the exponential moving average models seem to converge. And that just tells you how important it is to have a time series that is stationary. So a quick comparison of starting points for each method. So in the naive, of course, we take the actual value and then we move that forward. That's the forecast value for the next period. So in this case, 1451 just moves over, and that becomes the forecast value for, in this case, the year 2001. The simple moving average, in this case, we used a 3-period simple moving average. We just take those 3 values, add them together and divide, and then we have a forecast value in 2003 of 1,545. In the weighted moving average, we just multiply by the weights we have chosen. Remember, we chose 0.15, 0.35, and 0.50. So we just multiply and then add, and we get a forecast value of 1,585. Then for the EMA, with an alpha of 0.8, it starts like this. The EMA is a bit different in how it starts. So we begin by taking our first actual value of 1451. That moves into the forecast position for 2001. That's the starting point. Then we take our alpha of 0.08, multiply that by the actual value from 2001, plus the difference, or the dampening factor, of 0.2 times the forecast value of 1451. 0.8 times 1499 plus 0.2 times 1451 gives us our first value in the time series in terms of forecasting of 1489. And then we just continue that process all down the time series. So a quick warning about software: not all moving averages are the same, and your software doesn't know that. So just keep in mind that there are many generic moving averages that are used in many disciplines, but the way we apply them in time series is a bit different. What might happen is you might do software where it'll try to put the first forecast value in the wrong place. So you don't want it to do something like this. We want it to do this, where it actually puts the value in the correct first forecast period. And of course, Excel is notorious for this. Make sure you put your first forecast value in the correct time period, otherwise the entire time series will be off. So let's run this process down the entire time series. You can see that what we're doing is multiplying the actual value by our alpha of 0.8, and then the forecast value on the right by the dampening factor, or the difference, of 0.2. And we go down the time series and do the entire thing. So the forecast for 2021 is going to be 0.8 times 2396 plus 0.2 times 2506, and that has a forecast value of $2,418 per capita. So graphically it looks like this. The green line is our actual data, and the pink dot is our actual. Looks pretty good to me. So we made the forecast, but we haven't talked about errors yet. Forecast errors create a new derivative time series that can be a treasure trove of information for the analyst. Remember the gap between the actual line and the forecast line in our previous graphs? Those are our errors. By looking at just the forecast errors, you should be able to reverse engineer how the underlying time series looks. In fact, many forecasting techniques do this very thing under the hood. So patterns in the errors can reveal trend, seasonality, inflection points, and so on. And examining forecast errors can help in the selection and interpretation of other forecasting techniques. So there is a ton of information in the forecast errors that you should analyze. Here are the naive forecast errors, which in this case is the same thing as alpha equals 1, so we can think of it as that as well. Notice our forecast errors on the left are positive, on the right they are negative. On the left we are under forecasting, on the right we are over forecasting. Now again, on the next few slides, what I've done is morphed them together. So let's look at how they change as the forecasting method changes. So here is the 3-period moving average forecast errors. Notice they are a lot larger. So the 3-period simple moving average didn't do very well. The errors are quite large. There are the weighted moving average forecast errors, a lot better. You can see that the bars went down on the left and down on the right. Of course, they're upside down, they're inverted, but the errors got smaller when we moved to a weighted moving average. And remember, in the weighted moving average, what we did is we weighted the more recent values the heaviest at a weight of 0.5, then 0.35 backward one period, and 0.15 backward the third period. Now let's see the exponential moving average with an alpha of 0.8 we've been working on. Great, well the bars got smaller. So on the left, they went down. On the right, they're inverted, but they went down as well. So it appears that the exponential moving average with an alpha of 0.8 is better than the weighted moving average we did with weights of 0.15, 0.35, and 0.5. And think about it for a second. That should make sense. What we're essentially doing is taking the prior period, and instead of weighting it 0.5, we've weighted it 0.8. We put more weight on that prior period actual value. In theory, should be better because we have a trend in the time series. So when we compare all these methods, the orange bars are the naive forecast errors. We can see those as they go across the screen. And then what we'll do is add the other forecasting methods as we go. The gray ones here are the 3-period simple moving average forecast errors. We can see that they're quite large. So the simple moving average did not do too well. Here in the orange, we have the weighted moving average errors. The weights were again 0.15, 0.35, and 0.5. It did better. And then finally, we have the exponential moving average errors. Look at where those fall. We can see that of the methods, it's definitely the best relative to the naive. So the errors there in the orange are pretty much all smaller than the gray for the simple moving average, the orange for the weighted moving average. The blue bars for the errors of the exponential fall between the naive and the weighted. So it appears that of these 4 methods for forecasting, the naive in this case is the best, and then the exponential is the second best. And again, that should not be a surprise because our data has a strong trend to it. So here are the actual values versus the forecasts that we would create. So this blue dotted line is the actual GDP per capita for Nigeria, the naive forecast in the orange, the 3-period simple moving average forecast in the gray, the 3-period weighted moving average there in the yellowish color. Notice that it falls between the naive and the simple moving average. And then finally, we have the exponential, and it falls between the weighted and the naive. So we can see that the exponential is an improvement. Due to the strong trend, the naive forecast continues to be the best. But where do the forecasts seem to converge? Well, right there around 2017. Why? Well, that's where the time series flattened out. And I'll hammer this into every video I do on this. That is why it is so important when we're doing these forecasting methods. If the forecasting method requires a time series to be stationary, it must be stationary. And there are ways to do that. But notice in this case, once the time series sort of flattened out, they all converged right there around 2017. Here's the same graph just zoomed in so we can see the lines a bit better. We can see that, again, the exponential moving average falls between the naive and the weighted. That's because we weighted the actual values more in the exponential. So here we have our forecast accuracy matrix, sort of our scorecard of our forecasting method, so we can keep track of how each one of them does. We have added the exponential moving average there on the 4th row. We can see that for the MAE, or the mean absolute error, the exponential moving average, again, falls exactly where we would expect it to. It is better than the 3-period weighted moving average above it, but not as good as the naive forecast method at the top. Same thing for the root mean square error. It falls in the exact same spot. Same thing for the mean absolute percentage error. It falls in the exact same spot. Remember, the maze is a comparison to the naive forecast. That's why the naive forecast maze is 1. And therefore, with a maze of 1.24, we can say that the EMA is worse than the naive forecast, but it is better than the other two above it. And the same story for SMAPE, the symmetric mean absolute percentage error. It falls right in the same order. So it would appear, we can see here, that our exponential moving average is better than the weighted, but not as good as the naive due to the trend in the data. Okay, that wraps up this video on the exponential moving average. We went over the conceptual part of it. We went over many graphs. We saw some animations. So hopefully you understand how the exponential moving average works and some of the pitfalls that can happen in this and other techniques when there's a strong trend in the data. And of course, we will get to the point where we can take the trend out, or at least account for it using some other method that will make our forecasts a lot better. So, thank you very much for watching this video. I appreciate your time very much, and I hope you learned a lot. I will see you again in the next video. Take care and bye-bye.